Record. Okay, so we're going to do problem 1 from section 7.9. And in this problem, we're given the matrix A is 2, -1, 3, -2, and we're also given the vector G, which is a function of time, is given by e to the t and t. And what we're asked to do is we're asked to find the general solution to the non-homogeneous system of ODEs given by x dot equals ax plus g. So this is a little bit different than the problems we've looked at up to now because we haven't had this vector g here. Okay. So that's what we're asked to do. And we're going to solve this problem in a slightly different way than we have the other ones. We're going to use the method of diagonalization. Okay? So we're still going to have to find eigenvalues and eigenvectors, but what we're going to do with them is we're going to construct a matrix transformation that allows us to rewrite this system as an uncoupled system of ODEs. Okay? So, so the general strategy is we're gonna write x as some matrix times y, and then we're going to plug that into this differential equation. So we get x dot is equal to sy, and s is going to be a constant matrix. It's not going to depend on time, so that's just going to be sy dot. And on the other side of this equation, what we're going to get is ax plus g equals a times sy plus g. And this equation tells us that these two things are equal. And so what that gives us is that sy dot equals a sy plus g. And we're going to pick s so that s is non-singular, so that it has an inverse, which means we can write this as y dot equals s inverse a s y plus g. And so this matrix right here, what we're going to do is we're going to not only pick s so that s inverse exists, so that it's non-singular, but we're going to pick s so that when we multiply s inverse times a times s, we get a diagonal matrix D. Oh, I'm sorry. I forgot right here. I multiplied by s inverse, so right here I need an s inverse G. So then what we're going to be left with, if we can find an s like this, we're going to be left with y equals dy plus s inverse G. And because this matrix is diagonal, we're effectively going to have decoupled our system into a system that's y1 equals, let's say that d is equal to lambda 1, lambda 2, 0, 0, then this is going to be lambda 1, y1 plus, we're going to have to compute this thing and take the first component of it, and y2 dot is going to be lambda 2, y2 plus s inverse g, again, and it's going to be the second component of it. And so what we're left here is this differential equation depends only on y1 and not on y2, and this differential equation depends on y2 and only on not on y1. So these two are decoupled, and we can just solve them separately using methods for solving differential equations that you guys learned in your previous class. So that's the basic strategy that we're going to use here. And in order to do it, we need to find this S and this matrix D. And so that amounts to diagonalizing A, right? And we learned already that if matrix A is diagonalizable, which it will be as long as A is not defective, then we can always find a matrix S and a matrix D such that D along the diagonals are eigenvalues of the matrix A, and the matrix S is constructed from a matrix constructed with the columns as the eigenvectors corresponding to these eigenvalues. Okay? And so, again, what we have to do is we have to find eigenvalues and eigenvectors. So, the first step, let's find our eigenvalues. And the way we find eigenvalues is we want to find, we're solving the system that A V equals lambda V, right? And so we want this system to have a solution for V which is not 0. And the only way that's possible is if the only way this is possible is if A minus lambda I is singular. And the way we can make sure that it's singular is we impose the condition that the determinant is 0. So this is what we're going to look for to construct our characteristic polynomial. Okay, and so let's write that out. Is equal to the determinant of 2 minus lambda minus 1, 3, and minus 2 minus lambda. Okay, and so that is equal to this times this minus this times this. So that gives us 2 minus lambda times minus 2 minus lambda, and minus 3 times 1, so that just gives us plus 3. And we want that to equal 0. And so what we can do is we can multiply this out, and we get negative 4, that times that, plus 2 minus 2. So the lambda term cancels out, and we have this times this, which is plus lambda squared, and we have plus 3. We want that to equal 0, and so we can factor this out. We can combine this. This becomes lambda squared minus 1 equals 0, and that tells us that lambda minus 1 times lambda plus 1 is 0. And now we have the solutions. This is, it can be 1 or minus 1. Okay, so these are our eigenvalues of A. And now let's use these eigenvalues and find eigenvectors associated with each eigenvalue. And again, the eigenvectors we find by, they will be formed from the null space of this matrix right here. Okay, and so the way we find elements of this null space is we say that this matrix times V equals 0. So let's write that out. So let's do this first for lambda equals 1. And what we're looking for then is this matrix when lambda equals 1 becomes 2 minus 1 is just 1, minus 1, this is stays 3, and minus 2 minus 1 is minus 3. times v1, v2. And we want that to equal 0. And you'll notice with all these problems, once we plug in the right eigenvalue, we have some repeated information in these two equations. And in fact, these equations are just multiples of each other. And so we can just read the solution from the top equation. That tells us v1 minus v2 equals 0, or v1 equals v2. And so our eigenvector has, if v1 is 1, then v2 has to be 1 as well. So it's this vector or any multiple of this vector. So the null space is a span of this vector. Okay? And now we've done this for lambda equals 1. Now let's find the eigen vector for lambda equals minus 1. And in that case, this matrix right here, A minus lambda I, becomes 2 minus negative 1, so that just becomes 3. This is minus 1, and this stays 3, and this becomes minus 2 minus negative 1, so that just is minus 2 plus 1, which is just minus 1, times v1, v2, and we want that to equal 0. And same thing, in this case, the two rows are identical, the two equations are identical, and we get 3v1 minus v2 equals 0. So that tells us v2 equals 3v1. And so if v1 is 1, then v2 will be 3. So our eigenvector for this eigenvalue is, if v1 is 1, then v2 will be 3. It's this vector or any multiple of this vector. So the null space is spanned by this vector, is the span of this vector. And so what we have are eigenvectors and eigenvalues for our two eigenvalues and the eigenvector associated with each one. And right here, I should point out that each of these has algebraic multiplicity 1. So we know that this matrix is not defective, and so we can diagonalize it. And so let's write down what these matrices should be. So what we have, our matrix D, are just eigenvalues along the diagonal. So let's take 1 minus 1. And our matrix S is the eigenvectors for each eigenvalue as columns. So the eigenvector associated with 1 is 1, 1. And the eigenvector associated with minus 1 is 1, 3. Okay, and so we have S and D, and this part that I just erased, what we noticed is that we also need to know what S inverse is to do this procedure. So let's compute S inverse. And we know if S is invertible, in order for S to be invertible, we should check that it is invertible. And to check that, we just check that the determinant is not 0. And so determinant of S is 3 minus 1, so that's not 0. It's not 0, so it is invertible. And if it's invertible, one way we can find the inverse is by augmenting S by the identity matrix and row reducing it. And what we'll be left with is I on this side, and on this side will be S inverse. Okay, so let's do this calculation. 1, 1, 1, 3. Oh yeah, it's still recording, good. 1, 0, 0, 1. Okay, and so what I'm going to do is I'm going to take negative row 1 and add it to row 2 and put it into row 2. So that's going to keep row 1 the same. And that's going to give me 0, 2, minus 1, and 1. And now I'm going to take row 2 and divide it by 2. So I can make this 1. And so that's going to give me 1, 1, 1, 0, 0, 1, minus 1 half, 1 half. Okay? And now I'm going to take minus row 2 and add it to row 1. Okay, so I get 1 here, and subtracting 1, this becomes 0. So this becomes adding plus 1 half to 1. So I get 3 halves. And this becomes subtracting 1 half. So I get minus 1 half. And then here I have 0, 1, minus 1 half, 1 half. Okay, so now this is identity. And so this is S inverse. And let's just check that we didn't make a mistake and that this is actually S inverse. And so to do that, we can just actually multiply S times S inverse. And that will give us that'll give us 1, 1, 1, 3 times 3 halves minus 1 half minus 1 half 1 half. Okay? And so let's do that out, this multiplication. The element here, there are 4 elements that we need to do. And the element here is this top row times this first column. And so that becomes 3 halves minus 1 half, which is just 1. This element right here is the top row times the second column. So that becomes minus 1 half plus 1 half, so that's 0. This element right here becomes the bottom row here times the first column. So that becomes 3 halves minus 3 halves, so that's 0. And this one right here is the second row in the first column. So the second row times the first column, that becomes minus 1 half plus 3 halves, so that's just 1. And so that gives us the identity. Great. So now we have S, and we have S inverse is this matrix. And so let me just erase this part here. Oh, well, you know what? Why don't I write it here for summarizing? So I have D equals 1, 0, 0, minus 1. S is equal to 1, 1, 1, 3. And S inverse is 3 halves minus 1 half minus 1 half 1 half. Okay. So now that we have all this information, we can solve our system by diagonalization. So let's erase this part right here. And so as we just talked about, we're going to take x equal to sy, and then we're going to write our differential equation in terms of y. So that tells us that sy dot is equal to a sy plus g. And then we know S inverse exists, so that tells us y dot is equal to S inverse a s y plus S inverse g. And this, of course, is d. So our differential equation in terms of y dot is y dot equals 1, 0, 0, minus 1, y, plus S inverse, 3 halves, minus 1, minus 1 half, and 1 half, times g, and our g is e to the t, and t. Okay, and so that reduces to y1 dot equals y1. In fact, why don't I write this? y1, y2. So this is y1, and plus, this is going to be 3 halves e to the t minus t, 1 half t. So plus 3 halves e to the t minus 1 half t. And y2 dot is equal to minus y2. And here we do this second row. So it's minus 1 half e to the t plus 1 half t. Minus 1 half e to the t plus 1 half t. Okay, so now this is a decoupled set of ODEs and some new variables y. So now what we're going to do is we're going to solve the system of ODEs in y, and then we're going to use this right here to transform back to x. So how do we solve this system of ODEs?